So this is the first video for the introduction to our covalent compounds unit. And so what we're going to cover in this video is what is the definition of a covalent compound, what are just some basic properties, and then the most important thing that I need to go over is how do you draw a Lewis dot structure for what a covalent compound looks like when it starts to form. So what is a covalent compound? I can spell, I promise. So a covalent compound, the reason compounds form, the reason elements get together to make compounds is because they're trying to fill their valence shell. They want to have a full valence shell. So compound just means two or more elements bonded together. And there's different types of bonds that they can form. And covalent bonds is one of those types of bonds. And so specifically for covalent bonds, what's happening is this is when elements share their electrons, and they share them in a way so as to satisfy all atoms' octets. So what that means is that all atoms want to have 8 valence electrons. So if they don't have 8 valence electrons, they can bond with another atom and then share their electrons in a way so that they all have 8 valence electrons. There's a couple like little exceptions that we got to know about this. And those are that hydrogen and helium don't need 8. They only need 2 valence electrons. They are satisfied with a total of 2 valence electrons. And then it is possible for some atoms to have what's called an expanded octet. And all that means is that they can have more than 8. We don't attempt to put more than 8 valence electrons on them if we can satisfy them with 8 some other way. But if the only way to satisfy every octet requires that an atom has a couple more than 8 electrons, that's okay. And that will make sense when we get into drawing Lewis structures. So the second thing we gotta go over is properties. So properties, just in general, these are kind of a memorization thing. Covalent compounds tend to have low melting and boiling points. They're non-conductive. So what that means is if you dissolve them in water, that solution that you make is not going to be conductive. It won't conduct electricity. And they tend to be kind of brittle. So just some general properties for you. So now let's talk about how do you draw a Lewis structure. So the first thing you got to do is look at the element and determine how many total valence electrons are present in that particular compound. I'm looking for my periodic table. So an easy way to determine how many valence electrons are in an element is we can use our periodic table as kind of a shortcut. Everything in group 1 is going to have 1 valence electron. Everything in group 2 would have 2 valence electrons. We can't use this shortcut for this middle section, but if you jump over here to group 13, everything in group 13 would have 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7, and 8, with the exception of helium. So everything in group 18 has 8 valence electrons except for helium, which only has 2. So you can use your periodic table as a hint and a shortcut to determine how many valence electrons. And something that I failed to mention up here, covalent compounds. These compounds, the only elements, the only atoms that tend to form covalent compounds or have a need to share electrons are nonmetals. So nonmetals are the only ones that, when they get bonded together, are forming covalent compounds because they're sharing their electrons. And as a reminder, nonmetals are the ones that, if you recall, there's like a stair step that's kind of in this region of the periodic table. Nonmetals is everything to this side of the stair step. So we're talking about a very small group of elements that are forming these covalent compounds. And hydrogen is also considered to be a nonmetal, even though it's over here. So it's just this top right corner plus hydrogen. Those are the ones that are going to be forming covalent compounds. So the first step in producing a Lewis structure is to count up the total number of valence electrons. Whoa, I'm sorry. Count up the total number of valence electrons. So let's kind of do an example as we're working out the steps here. Let our example be CF4. So for CF4, if I check my periodic table and I find carbon, carbon's in group 14, which means it has 4 valence electrons. So we got 4 valence electrons for carbon. And then I find fluorine, which is right here. Fluorine has 7 valence electrons. So fluorine has 7 valence electrons, but there are 4 atoms of fluorine. So that's a total of 28 coming from those 7 valence electrons. So if I add up all of these valence electrons, that means I got 32 electrons total to work with. So the atom of carbon and the 4 atoms of fluorine are bonded together, sharing these valence electrons in a way so that everyone has a full octet. So the next thing you got to do is assign a central atom. There's kind of 3 sub-rules for this. If carbon is a choice, which it is for us, so if carbon is in your compound, carbon is always the central atom. If hydrogen is part of your compound, hydrogen is never the central atom. And then beyond those 2 rules, it's usually whatever's written first. So if you're reading the compound from left to right, whatever element is written first is going to be the one that's your central atom, the first element. Okay, so if I'm assigning my central atom, I'm going to choose carbon as my central atom. So I write carbon, and now I got 4 atoms of fluorine. So all I have to do is kind of spread those things out around my carbon as evenly as I can, which makes it look like that. The next thing you have to do is connect it together. So if we're making a compound, connecting this together means they're sharing some electrons. So I represent that by using a line. So a straight line means a pair of electrons. The line equals 2 electrons. So in making these connections, I've used up 8 electrons of my original 32. So I've used 8 electrons just in connecting it together because I have to connect it together. So I'm going to subtract that away from my original count. So 32 minus 8 leaves me with 24. So now I'm going to take an evaluation of what does it take to satisfy octets. And there's kind of three subparts to this. So if I look at this structure as I have it drawn so far, this fluorine is sharing 2 electrons, but remember the goal is to get everything to a total of 8 electrons. So if this fluorine is sharing 2, that means it would require 6 more to give it 8. And this fluorine, and this fluorine, and this fluorine are also they need 6 more to have a full octet. They need 6 more. If they're sharing 2, they require 6 more. So if I got 4 fluorines that all need 6 more electrons, that means I need to apply 24 more electrons to give these fluorines the full 8 that they need. Don't forget to also check your central atom. This carbon is sharing 8 electrons, and so it is what we would call satisfied. It has the 8 that it wants. Even though it's sharing them, it still has the 8 electrons. So since I need 24 more electrons to satisfy all of these fluorines, if I have the perfect right amount, then I'm done, and I can just give the fluorines the electrons that they want in the form of dots. And these dots represent electrons, and they always go in sets of 2. So by putting 6 dots, or 3 sets of 2, on each of these fluorine atoms, that is now satisfying everybody's octet, and I've used up the exact same number of valence electrons that I counted up to begin with, which was 32. So if you have enough, electrons, you just give them out. And we call those lone pairs. So we give them out as lone pairs. So these electrons are what we would call a lone pair, because it belongs strictly to the fluorine. It is not having to share those electrons. These electrons that are being shared is what we would call a shared pair. Shared pair. Okay, so if we have enough electrons, you just give them out as lone pairs. So what happens if you don't have enough electrons? So that's kind of the next situation. If you don't have enough electrons. So let's do another example, and I'm going to use the margin, that way I don't have to turn the page. Let's say we do O2 as our next example. So I have 2 atoms of oxygen. Oxygen is in group 16, which means it has 6 valence electrons. Since there's 2 of them, that means I got a total of 12. So I got 12 valence electrons total that I need to share between these 2 oxygens so that they can have full valence shells. In this case, assigning a central atom, there's only 2 atoms to begin with. So if there's only 2 things, you don't have to put anything in the, say, middle. The only thing these 2 atoms can do is sit side by side. The next thing to do is to connect them together. So I make a connection, and in that connection I've used up 2 electrons, which means I got 10 remaining. So since I have 10 electrons remaining, now I'm going to assess what it takes to satisfy everyone's octet. This oxygen is sharing 2 electrons, which means it would require 6 more. This oxygen is sharing the same 2 electrons, which means it would require 6 more. But we only have 10 remaining. So that falls into this category. We don't have enough electrons to satisfy the octets based on this particular structure. So what you have to do, what that means is they have to share more. And so by share more, that means we need to add another bond. So if we add another bond and make them share 2 more electrons, I'm going to remove those 2 electrons from my total count. So I started with 12. I made them share 2 originally. 10 electrons left over wasn't enough to satisfy all the octets, so I'm going to make them share 2 more. So now I have 8 electrons. So now I'm going to recount to see what it takes to satisfy the octets. This oxygen is sharing 4 electrons, which means it now needs 4 more to satisfy its octet. This oxygen is sharing 4 electrons, which means it now needs 4 more to satisfy its octet. So if I need 4 for this oxygen and 4 for this oxygen, now I have the correct amount, which brings me back to this first step. Once you have enough, you give them out as lone pairs. So since I have enough, I can give this oxygen 2 lone pairs, and I can give this other oxygen 2 lone pairs, and now both of them are satisfied because they have 8 total electrons, but I haven't exceeded the 12 that I had to begin with. So if I go through and I count 2, 4, 6, 8, 10, 12. This is what we would call a double bond. There is a such thing as a triple bond, but it never goes any higher than that. So you can have a single bond, like this one, or you can have a double bond like that, or it is possible for 2 atoms to have to share 6 total electrons, which would be classified as a triple bond. So we've done an example where we start out with the perfect amount right away. We've done an example where you don't have enough, and so we have to add another bond. What happens if you have too much? If you have too much, let's see what we have to do there. And I'm going to do another example just up here. Let's do BRF5. So BRF5. So if I look at the periodic table, I find that Br has 7 valence electrons because it's in group 17. Fluorine is also in group 17, so it has 7, but there's 5 fluorines, so that's a total of 35. And if I add 35 plus 7, I got 42 total electrons that I can share around to make this thing sharing the electrons in a way so that everything has 8. Next thing to do is choose a central atom. Carbon is not a choice here, so I can't put carbon in the middle. So I have to rely on the fact that whatever's written first becomes my central atom. So Br, and then I take 5 atoms of fluorine and spread them around. Next thing I have to do is connect them together. And by connecting them together, that uses up 10 total electrons. So now I got 32 left. This is the perfect example of what I was talking about right here, about having an expanded octet. The only way for me to get Br with 5 fluorines attached to it is for bromine to have 10 electrons coming off of it, which is greater than 8. And that is okay, because there is no other possible way for me to get bromine with 5 fluorines on it if I don't have bromine holding more than 8 electrons. So this is fine. So now I take an assessment of what it takes to satisfy the octets. Well, bromine has an expanded octet. It's got 10 electrons. So I don't need to try and give it any more. If it ends up with more, that's fine, but I don't need to give it more because it already has 8. Each of these fluorines is sharing 2, which means each fluorine needs 6 more electrons to make it to the magic 8 number. So if each fluorine needs 6 more, that means I need a total of 30 more electrons to be able to give each fluorine 6 more. And I have 32, which is too much. So if you have too much, you go ahead and pass out the lone pairs, because you've got enough to do that. So I'm going to give each fluorine the 6 electrons they need in pairs of 2. And then the thing you do with those extra 2 electrons is you just put them on the central atom. And it doesn't matter where you put them as long as you put them as a group of 2, because electrons always go in pairs. So if you have too much, you satisfy octets, then put the extras on central atom. So I'm going to give you kind of a list to practice, and that will be the end of this first video. So here are some that you can practice with. NH3, COF2, CH4, SF6, H2O, and that should do it. So practice those. You can, once you have them done, just Google Lewis structures and then type in each of these things, so Lewis structure of NH3, and compare what you got to the image that they provide you, and that's how you know if you're doing it right.